In the previous video, we talked about the center mass and we derived an expression for the center mass. We also talked about the significance of it, that how it actually makes easier for us the calculation of multi-particle system in physics. And now today we're going to solve the relation, we're going to find the relation between angular momentum and the angular momentum about center mass. For this, we consider again a system of particles here. Again, this is a multi-particle system, a lot of particles, but for simplicity, we are saying just one particle here. That is P. The point P here, the Ri is the position vector of the particle with respect to the origin, and let the mass of the ith particle be mi. Also, this is the center mass given by point Q. And capital R is the position vector of the center mass. Also, the position vector of the particle P with respect to center mass is given by Ric. Again, let the velocity of center mass be capital V. Also, let the velocity of ith particle with respect to the center mass be Vic, and the velocity of ith particle with respect to the origin be Vi. Again, of course, from the vector summation rule, we say that here R plus Ric equal Ri, because these two vectors sum over here and gives the sum Ri. And this implies that Ric equals Ri minus R, and V plus, in the same way, V plus Vic equals Vi, implying that Vic equals Vi minus the capital V, where capital V, of course, is the velocity of center mass with respect to the origin. And here, so we know that the angular momentum is given by mass into the position vector of the particle with respect to the point about which we want to find the angular momentum cross the velocity. And so using the equation 3, we can write the angular momentum of the system here. J equals sigma. And the sigma here is because this is a multi-particle system, and so we have to sum all the contributions from all the particles. So sigma is taken here. Applying the vector triple product rule and expanding this, we get J equals mi to V plus R cross sigma mi Vic plus well, so this is question 4a. Now, what property we have used here is that if there are three vectors A, B, and C, the scalar product of the three vectors, say A dot B cross C, can be written as B dot C cross A equal C dot A cross B. This actually follows a cyclic order here. And so now again, from equation 4, let's consider the term, this one, mi, the sigma mi Ric. We note that Ric equals Ri minus the position vector of the center mass, and this implies that sigma over m Ric equals sigma over mi. This is Ri minus sigma over mi into R. But as we note that, this is actually the expression, the mi Ri is mr, where m is the total mass of the system. We know it from what we calculated, the center mass, and this is actually the total mass. And so this becomes 0. So mi Ric equals 0. In the same way, we can show that mi Vic, that is the momentum, the total momentum of the system about the center mass is 0. And so equation 4 becomes J equals R cross mv. Of course, the m is the total mass of the system. Some sigma Ric cross mi Vic. Well, now let's a bit investigate these two terms here. Of course, this gives from our from here we can see that from this equation, the angular momentum is equal to m into r cross v, that it gives the angular momentum of the center of mass about the origin, and this one gives the angular momentum of the system of particles about the center of mass. So this can be written as A equals angular momentum of the system, the center of mass about the origin plus the center of mass plus the angular momentum of the system about the center of mass.